Hello. Okay, Ms. Walsh here. So we're going to do day 2, and we're going to do optimization. Okay, so remember with optimization, you're going to need to use your formulas, and you're always going to have two equations. You're always going to have the one that you optimized, and then you're also going to have your friend. That's the one where you actually get the information from that you can then use to isolate for a variable. Okay, so let's look at the first problem. The food company produces mozzarella sticks, and it can be modeled by this, and this should actually be changed. The volume of this is 81, so show that. So this is actually, you need to change this in your notes, show that the total surface area is given by this equation. Okay, so the first thing that we're given here is we're given that the volume of this cuboid is 81. So what that's going to be is that's going to be our helper function. If you look in your formula booklet, the volume is length times width times height. And in this, let's put it in the context of our variable. So that's going to be x times y. And we know that the volume is actually 81. So you're going to have 81 is equal to x squared y. Okay, so this is your constraint function. This is your helper. Okay, what do they actually want? Well, what they actually want is they want the total surface area. Okay, so let's set that up. Okay, so our surface area is going to be all the sides. Okay, so first we have two squares. So on the ends there, so that's going to be x squared, and there's two of them, and then all of these are equal. So that's going to be xy, 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 and you're going to have 4 of them, okay? So, if we could do multivariable work, you would be done. You would just find the minimum or whatever it is that they want. But the problem is that we've got this pesky y here, okay? So this is when we call back onto our helper function, and then what we're going to do is we're just going to always isolate for y. The way we do that is by dividing both sides by x squared, and we're going to end up with 81 over x squared. And so how that's going to help us is we're going to substitute it into our optimization function. So what we're going to have now, keep your eye on the price to see if we're, getting to where we're supposed to be. So that's 2x squared plus 4x, and then instead of y, we're going to write 81 over x squared. Okay, well, this is good. The 2x squared is already there. And then x on the top and 2x is on the bottom. What's going to happen is one of them is going to cancel out. And if you multiply, look at this. 4 times 81 is indeed going to be 324 over x. And so we're happy. We have shown that this is the surface area. Okay, so again, the process is always the same. You always get something with the information that you will always isolate, and you will substitute it into the function that you want. So then, now let's do b. Change it in your notes. It's c, and then this is going to refer to b. Okay, so now we just need the derivative. So remember, even if you are not able to do b, it's really important to be able to pick up those marks. So this is the derivative. You see that the x is on the bottom. So the first step that you want to take is you want to rewrite this, pull the x up. And remember, you have not derived. All you've done is you've just pulled it up, okay? Now, remember how to derive, so you're going to drop this. So this is going to be minus 324x, and then minus 1, that's 22, plus 2x squared, derived is 4x. Done. The surface area is to be minimized in order for the cooling rate of the mozzarella stick. You want your mozzarella sticks to stay as hot for as long as possible, I suppose. All right, use your answer in B. So that means you must use your answer in B to find that it minimizes. So remember, whenever you have the minimum or whenever you have the maximum, then your derivative is always 0. So that's what they want. They want to see that you recognize that the derivative is 0. So you're going to take your derivative, minus 324x minus 2 plus 4x, and you're going to set it to 0. And now, remember, when you set a function to 0 on your calculator, the function equaling to 0 is the equivalent of an x-intercept. So So let's put the function in. I'm doing a really terrible job of deleting these. Okay, so minus 324 times x to the power of minus 2, and then plus 4x. Okay. What's important to remember is that this is not the original function, okay? All of these are slopes. They're all derivatives. When you go to this is the derivative at 2. This is the derivative at 1, okay? Which is why it's perfectly fine for them to be negative. It just means that if you look here, you have a bunch of really steep negative slopes. Anyway, what we want is we want the root. Okay, great. So what you got is you got x is equal to 4.37, okay? So that's the value of x that you need in order for the surface area to be minimized. What you can do as well is you can always plot the original function, okay? But just don't tell them that you're doing it. What you're doing is you're getting the mark for your understanding of using the derivative correctly. But if you would like to, just throw that original one in. So I'm going to get rid of this one, and then I'm going to put on 3, 2, 4 over x. And then, don't look at the negative side. If your graph doesn't look very nice, you can always do view, auto scale, and then instead find the minimum, but don't draw it. Shh. What you would have to draw is you would have to draw the derivative, okay? So just find the extremum, and look, you get the same answer, right? You get 4.33. Did I get 4.37? Okay, whatever. But here, what you get then is you also get the area. So if they ask you what is this minimum area, then you also have that answer there, okay? So either way, either plot the derivative or plot the original. All right, and that's optimization problem number 1.